95, yeah, divided by 4. So this is the usual exam part, okay? The attendance, if you, each attendance here, that's the attendance is full score, okay? If you have one time, okay? One time, if you have one time not attendance, okay? If you have one time not attendance, we will minus 20, okay? Minus 20. So if you do not attend the class 2 times, okay? So your usual score is 0. Your usual score is 0, okay? So here, one time not attendance, minus 20, okay? So if you not attend the class twice, so the usual score is 0. If here is 100, oh, that is also 0, okay? Also 0. And if you have one time, late, okay? Minus 10, okay? Minus 10. So here for this part, okay? For example, for this part, your usual exam, the first is 70, 80, 85, 60. So we take the average. We take the average and times 14%, okay? And times 14%, and if you have one time later, so here minus 10. This is your usual score, okay? Your usual score. So if you have one time later, okay, minus 10. Yeah, if you have one time later and one time not attendance, so minus 10, minus 20. Yeah. So if you have two times not attendance, so here is minus 20, so here is minus, yeah, minus something, okay? So here means that, okay, if you have twice not attendance, that means you must have 100 score at the final exam, and you can pass this class, okay? So here this is this part, okay? And each time, okay, I here have your list. So local here, okay, local here. Now the last semester we introduced the chapter 4, yeah. So see page 200, okay, 200. This class we will introduce the L'Hopital's loop, okay. L'Hopital's loop and determinate forms, okay, determinate forms. So for here, we must recall the derivative, okay, the derivative. So what's the derivative? The derivative, okay. The definition of the derivative actually is f prime x. How to define? Actually, is the limit h approaches 0, f x plus h minus fx, yeah, divided h. So let h approaches 0. So this limit, if this limit exists, we say that the function f is derivative is definitionable at x. So this is the derivative of the derivative, okay? The definition of derivative. So now we have the continuous, okay? Continuous at a point x0. How to define it? How to define it? To define it, limit x approaches x0, fx approaches fx0. Yeah. So if when x approaches x0, fx approaches fx0. So if we have this limit, then we say that the function f is continuous at x0. At x0. This is the definition of the continuous. The definition of the continuous. So we have another definable. So the definable at x0. So if a function is definable at x0 means what? Means what? Here means limit h approaches 0 f x0 plus h minus fx0 divided by h. So if this limit exists, then we say that the function is definable at x0. Yeah. So what's the relationship between the continuous and the definable? So what's the relationship between the definable at x0 and the continuous at x0? So here actually we have a conclusion. If a function f is definable, a function f is definable at x0, this means what? This can imply f is continuous at x0. Yeah. But if fx is continuous at x0, does not imply f is definable at x0. Okay. Yeah. So here means f is continuous at x0 cannot imply f is definable at x0. Okay. So here we have the example. For this example, fx equal to the absolute value of x. This function, okay, this function is continuous at x0 equal to 0. This function is continuous at this point, but this function is not definable at x0 equal to 0. Okay. Yeah. So this is the relationship between the definable and the continuous. Okay. Yes. Continuous. So here now we record the derivative of some usual function. Okay. Some usual function. First is here. The fx plus gx, the derivative of f plus g derivative equal to what? Equal to the derivative of f plus the derivative of g. Yeah. So here is the first. The second, the derivative of f minus g derivative. Okay, f minus g derivative equal to what? Equal to f derivative minus g derivative. Yeah. And the third, fx times gx. Fx times gx derivative, okay? Equal to what? Equal to what? Equal to f derivative times g, yeah? Plus fx times g prime, yeah? So, and number 4, the fx divided by gx. So, for this derivative, equal to what? Equal to gx squared, the denominator, yeah, the denominator gx squared. The numerator is what? F prime minus g, times g, yeah? Minus fx times g prime, yeah? So this is here, and now for number 5, for example, here is a constant. Is a constant times a function derivative equal to what? Actually, this is equal to cf prime, yeah? So actually, you can see c as a function, and use the number 3, yeah? Because c prime, a constant prime is what? 0, yeah? 0. So actually, this part is 0. So this part is 0. So here is c g prime, yeah? So this is number 5 and number 6. Number 6. So here for a computation, okay? For a computation, for example, y equal to fu, u equal to gx, u equal to gx. So what about the derivative of dy dx? Dy dx. Actually, y is a function of u is a function of x. So actually, y is a function of x. Yeah, y is a function of x. So here we can see y, the derivative of y dy dx equal to what? Equal to dy du times du dx. Yeah? Times du dx. So here, actually here we can write it in this form, okay? So f composition here, this derivative, okay? This derivative equal to what? Equal to f prime evaluate at gx times g prime. Okay? So this and this, they are the same, okay? They are the same. They are the same. Yes. Now let's call. So here we will use the derivative of some usual function. For example, a constant derivative is what? 0, yeah? And so x, the power function, x to the nth power. So derivative is what? Is n x n minus 1, yeah? N minus 1. So here, and now let's see this function. Ex, the exponential function, ex derivative is what? Is ex, yeah? Is ex. And the ax derivative is what? Is ax ln a. Yeah? Here a is greater than 0 and a not equal to 1. Okay? And a not equal to 1. So here ax derivative equal to ax ln a. Okay? So here you can see here, if a equal to e, okay? If a equal to e, ex derivative equal to ex ln e. Ln e is what? 1. 1, yeah? Ln e is 1. Yes. So here actually, here. So now, and for example, for this function, ln ln x derivative equal to what? Ln x derivative equal to 1 by x. 1 by x. Yeah? And the function log of base a, or log of base ax, this derivative equal to what? Equal to x times ln a 1 by x times ln a, okay? So here, and now we have some other functions, For example, for this function, sin x derivative equal to what? Sin derivative.
Sin derivative equal to
Cosine, yeah?
yeah.
Yeah, cosine x. And cosine x derivative minus sin, yeah? Minus sin. And tangent x derivative what?
Minus cosine.
Second x square, yeah? Second x square. Actually, for here, for tangent x, okay? Actually, we know tangent x equal to what? Equal to sin x divided cosine x, yeah?
Yes.
So here, actually, the derivative of tangent x actually is sin divided by cosine derivative. Actually, you can use this formula, yeah? We use this formula. So here, you can see here, second x. Actually, second x is what? Second x actually is 1 by cosine x. Yeah? 1 by cosine x. So here is tangent x derivative, okay? So here cotangent x derivative equal to what? Equal to minus cosecant x square. Yeah? They are the same, okay? Cotangent x actually is what? Cotangent x actually is cosine x divided sin x. Yeah? Divided sin x. And cosecant x actually is 1 by sin x. And now actually we have second x prime. Okay, second x prime is what? Is actually second times what? Second times tangent. Okay, second x times tangent x, and cosecant x prime equal to what? Equal to cosecant x times or minus cotangent x. So this is this part, okay? So here, this is this 6, okay? Now we have another for arc sine derivative. Arc sine derivative is what? Is 1 by the square root of 1 minus x squared.
Yeah.
Okay, and arc cosine x derivative equal to what? Minus 1 by 1 minus x squared. And arc tangent x is 1 by 1 plus x squared. And arc cotangent x derivative is minus 1 by 1 plus x squared. Okay, so here, now, okay, all of you must remember these results, okay? Must remember, keep in mind, okay? Keep in mind. Of course, I will test this, okay? And we will use this. We will use this on this part, okay? Lopitas group, okay? So all of you keep in mind, okay? Keep in mind and remember it. So now, so here, With this results, now we come to L'Hopital's rule, okay? L'Hopital's rule.
네.
Okay, here, so here. So, okay, clear here? Yes. So here, now let's see a limit. Now let's see a limit. For example, for this limit, limit x approaches 0, sin x divided x, and the limit, the second limit, x approaches 1, x squared minus 1 divided x minus 1. Okay. Now let's see these two limits. For the first limit, okay, actually this limit is what? This is one of the two important limits. Yeah? So this limit is what? Is what?
Can you explain last four?
Last forward. Here? So
just the arc and arc.
Well, arc sin actually is the inverse function of the sin. Here is the inverse function of sin, inverse function of cosine, inverse function of tangent, inverse function of cotangent. Okay. So here, this limit actually is what? Is 1, yeah?
Yes.
Now let's see this limit. Actually, we have for you can see here the numerator here is the limit x approaches 0, sin x approaches what? Sin 0, yeah. So sin 0 is what? 0, yeah. So here actually here is 0, and the limit x approaches 0. This denominator x approaches what? 0, yeah? So actually here is the numerator is 0, the denominator is 0, 0 divided by 0, okay? 0 divided by 0. So this is the first. Okay, now for the second here, now we can see x approaches 1. So this limit actually is what? Is the limit x approaches 1, and here is x squared minus 1. X squared minus 1, actually we can rewrite it x minus 1 times x plus 1, yeah? Divided x minus 1, yeah? So here x minus 1 cancel, yeah? So here this limit actually is what? Is the limit x approaches 1, x plus 1 approaches what? X approaches 1, x plus 1 approaches what? 2, yeah? So here now let's see this limit, okay? This limit, okay? We have the numerator limit x approaches 1, x squared minus 1 approaches what? X approaches 1, x squared minus 1 approaches what? 1 squared minus 1, yeah? So here is what? 0, yeah? 0. And here the denominator x approaches 1, so x minus 1 approaches what? Also 0, yeah? So here means what? Here is 0 divided by 0, yeah? So here we have a question. For example, for this, when limit x approaches a, fx approaches 0, if x approaches a, fx approaches 0, and limit x approaches a, gx also approaches 0. x approaches a, fx approaches 0. X approaches a, gx also approaches 0. So here, we have a question. What about the limit fx divided by gx, where x approaches a? So what about this limit? So we have a question. The question is, we know when x approaches a, the numerator approaches 0, and when x approaches a, the denominator also approaches 0. So here actually it's 0 divided by 0.
Yes.
So what about this limit? What about this limit? So here in mathematics we call this form. Okay, we call this form of indeterminate form of type 0 divided by 0. So here this form, okay, this form we have a name. The name actually is indeterminate form of type 0 divided 0. Okay. So this limit, okay, this limit in mathematics we call it as the indeterminate form of type 0 divided 0. So how to find the limit of 0 divided 0? So we have a L'Hopital's rule. Okay, so the L'Hopital's rule. So now let's see the result. Page 201. 4.4.1. Okay, so here we have this result. So here. here, this is the L'Hopital's rule, okay? So now we can see it. Suppose that the function f and the function g are definable, so definable, okay? Definable functions on an open interval. This open interval must contain x equal to a, okay? Must contain x equal to a, except possibly at x equal to a, okay? So here, this means that the function cannot be definable at this point, okay? At this point. But the function must definable on an open interval, okay? And that if x approaches a, if x approaches 0, and x approaches a, gx approaches 0. So these two conditions, okay? So these two conditions means that this limit is an indeterminate form of type 0 divided 0. Okay? So here, if limit x approaches a, f prime divided by g prime, if this limit exists, okay, or if this limit is plus infinity or minus infinity, okay, so then we have what? This is the conclusion. The conclusion tells us that the limit of x approaches a, fx divided gx. This limit is equal to limit x approaches a, f prime divided g prime, okay. So the condition is this limit must exist. Okay, this limit must exist. This limit must exist. Okay. So moreover, this statement is also true in the case of the limit as x approaches a minus or x approaches a plus, or x approaches minus infinity or x approaches plus infinity. Okay. So here means what? Here x approaches a, we can change it. X approaches a minus or a minus. Okay. So one side limit is also true. Okay. Or x here you can change here a actually is x approaches plus infinity, x approaches plus infinity, plus infinity, plus infinity, plus infinity. Okay. So here this means that. So about this rule we have three remarks. Okay, the first remark is here. Remark. So here now let's see this limit. Limit x approaches 0, x plus 6 divided x plus 2. So this limit, okay? So this limit we use the L'Hopital's rule, so equal to what? Equal to limit x approaches 0, x plus 6 derivative x plus 2 derivative. So here is limit x approaches 0. This derivative is 1. This derivative is 1. So the limit is 1. So it's right or wrong. So this is right or wrong. So you can see here it's a x plus 6 divided by x plus 2. So this limit. So here we use the L'Hopital's rule. So it's equal to the derivative divided by the derivative, the limit. So here the derivative is what? Is 1. This derivative is also 1. So 1 by 1 is 1. So the limit is 1. So it's right or wrong? So it's right or wrong?
No, wrong, because that example is not in the determinate form.
Yeah. So what's your question?
Oh, I just want to know why the derivative of x plus 6 derivative and x plus 2 derivative is 1. Why?
X plus 6 derivative actually is x derivative plus 6 derivative. X derivative is 1, 6 derivative is 0. So fx plus gx derivative equal to f prime plus g prime. Okay. So this is right or wrong?
Wrong.
Of course, this is wrong. Okay. So why? So here we can see we have a condition. Okay. So this L'Hopital's rule just vivid for the indeterminate form 0 divided by 0. Okay. So here is 0 divided by 0.
No.
X approaches 0. X plus 6 approaches what? 6. Yeah. This approaches what? 2. So here is not 0 divided by 0. Yeah. So here we cannot use the L'Hopital's rule. Okay. So this is the first remark. The remark actually is the L'Hopital's rule just vivid for the indeterminate form of 0 divided by 0. Okay. So these two conditions must satisfy. Okay. The function must satisfy these two conditions. Okay. So this is the first remark. So actually here this limit actually is what? Is 6 divided 2. So this limit actually is 3. Okay? 3. So this is the first remark. The second remark is here. Now we can see limit x approaches 0. X approaches 0. Ex minus 1 divided x cubed. Okay? X cubed. So here, this limit, okay? This limit, now let's see. This limit is 0 divided by 0. Now we can see when limit x approaches 0, ex minus 1, this limit is what? Actually, this function is a continuous function, yeah? So here actually is e to the power 0 minus 1. So e to the power 0 is what? 1. So 1 minus 1, so 0, yeah? And so the numerator, the limit of the numerator is 0. So what about the denominator? So limit x approaches 0, x cubed is 0 cubed, so 0, yeah? It's also 0, yeah? So 0 divided by 0, so it's a indeterminate form of 0 divided by 0. So we can use the L'Hopital's rule, yeah? So the L'Hopital's rule is equal to what? Limit x approaches 0, ex minus 1 derivative, yeah? Divided by x cubed derivative, yeah? So here, this derivative is what? So this derivative actually is x approaches 0. This derivative actually is ex. Yeah?
Yeah.
This is 3x squared. Yeah? So here we can see here. Now, here this part, okay? So now we can see limit x approaches 0, ex approaches what?
Approaches 1.
Approaches 1, yeah? So the denominator x approaches 0, 3x squared approaches what? 0, yeah? So actually it's 1 divided by 0, so this limit is what?
Infinity.
1 divided by 0, infinity, yeah?
Infinity, yes.
So this time this approaches 1, and the denominator will be small. So here actually is 1 divided. So actually here is square. So here actually is plus 0. Yeah, plus 0. 1 divided plus 0. Actually is plus infinity. Yeah. So this limit actually is plus infinity.
Yes.
So here this remark, I want to say that this limit, if this limit exists, okay, or if this limit is plus infinity, or this limit is plus infinity, we also have this conclusion, okay?
Yeah.
When this limit is plus infinity, we also have this conclusion, okay? So this is the second remark. Now let's see the third remark. Now let's see this limit. Limit x approaches the third remark, okay, the third remark actually, I want to say one thing, okay? One thing means that this is the conclusion, okay? This is the condition. Condition means when this limit exists, we have this conclusion, okay? So So actually here means that sometimes, okay, sometimes we have a case. In this case, we have this limit, okay? This limit does not exist. But this limit exists. Okay, this limit exists. So here actually, you can see here, if this limit exists, we have this conclusion, okay? We have this conclusion. But sometimes when this limit does not exist, so what about this limit? So when this limit, f prime divided by g prime, this limit does not exist. Sometimes we have this limit also exists, okay? So I will, for this remark, I will give an example in the next section, okay? In the next section. So here now let's see some example, okay? So now, class is over. So we will have 2 minutes, yeah?
Yeah, we have 2 minutes.
So here now. Now let's see this example, okay? The first is limit x approaches 0, sin 2x divided x. The second is x approaches 1/2 pi, okay? 1/2 pi, 1 minus sin x divided cosine x, okay? The number C is x approaches 0 from left, tangent x divided x square. And here is x approaches 0, 1 minus cosine x divided x square. And the number E is the limit x approaches plus infinity, x minus 4 by 3, okay, divided by sin 1 by x. So this five examples. So we have a rest 10 minutes, okay? So look here.